This Filmmaker IQ lesson is proudly sponsored by Rode Microphones, premium microphones and audio accessories for studio, live, and location recording. Hi, John Hess from FilmmakerIQ.com, and today we're going to dive into the science and engineering of sound and microphones. As vision is our brain's response to electromagnetic radiation in the form of light waves, sound is our brain's response to atmospheric pressure changes. Well, we're not exactly walking weather barometers, but the concept is the same. Now let's imagine a tightly wound string, that of a guitar. When the string is plucked, the string vibrates, pushing the air molecules around it. This push is called compression, and it creates a peak of high air pressure. Now, as the string retracts, we have rarefaction, a trough of low air pressure. Now, this repetition of compression and rarefaction creates what's called longitudinal waves or compression waves. That's a wave where molecules are moving in the same direction as the wave itself. Now, it's worth noting that the molecules pretty much stay in one place. It's the energy that is moving through the air at the speed of sound. Now, if we plot the changes in air pressure created by the sound wave against time, we get a waveform. Through waveforms, we can visualize some key aspects about sound. The first is amplitude. Now, amplitude is the strength of the wave itself. The greater the distance from the center line, the more intense the wave. A common method of describing amplitude is something called RMS, root mean square, which is a mathematically handy way of determining the average amplitude of a wave. Well, then there's frequency, the rate of how many cycles of peaks and troughs are in a given period of time. Now, this is most commonly measured in hertz, or cycles per second. 1 hertz is 1 cycle per second. As we go up in the number of hertz, we perceive a rising in pitch. Now that we have a basic grasp of what sound is and how to describe it in terms of frequency, phase, harmonic content, and envelope, let's go back and look at amplitude or loudness. How do we measure the strength of sound? The human ear has quite an amazing ability to detect sound waves, capable of an energy range of approximately 10 to the 13th power to 1. With such an enormous range, we have to use a logarithmic scale in order to define loudness when working with audio. Now, fortunately, our ears respond to sound in a logarithmic fashion. The unit used to describe sound loudness is the decibel. Originally implemented by Bell Laboratories to describe signal loss in telephone lines, the decibel, which was formally introduced in 1928, describes the relationship between two different signals as 20 times log of the signal strength using root mean squared divided by a reference signal strength using root mean squared. Now, right off the bat, the decibel is not a measurable unit like a centimeter or a centigrade or a gram. It's a comparison, and you always need a reference. For determining loudness of sound pressure, we can use the quietest sound that can be detected by the average human being as our reference. This number has been internationally agreed upon as 20 times 10 to the negative 6 pascals, or 20 micropascals. Now, we can compare the sound pressure of noisy things to this bare minimum, and we can derive a decibel chart from a soft whisper at around 30 decibels SPL, to a freight train at 100 feet, which is 70 decibels SPL, to a jet takeoff at 200 feet, registering at 120 decibels SPL. Now notice the distance is always notated as sound waves dissipate according to the inverse square law. Now, safety regulations have risen around these decibel ratings, 85 decibels and below, and you'll be fined in that noisy situation for up to 8 hours. Cut that time in half each 5 decibels. You go up. But sound pressure level is only one kind of decibel. For filmmakers, we are more likely to encounter decibels in regards to the power of an audio signal when carried through an audio system. But the dBm is the most common expression used in audio equipment and audio workstations. There are a few basic concepts that are relatively easy to grasp. Turning up something by 3 dB will double the signal strength. But because our ears are so logarithmically sensitive, doubling the strength doesn't mean we double the loudness. Consequently, turning down something 3 dB halves the signal strength, which is also not as significant as you might think. And because we are using log, turning something up by 10 dB means we're actually increasing the signal 10 times. 20 dB, and we're increasing the signal 100 times. 30 dB boost means the signal is being boosted 1,000 times. Now, does this math matter to the working professional? Probably not. But as you work in audio, you will start to intuitively know what a boost of 3 dB sounds like, or 6 dB. Just know that there is a tremendous amount of science, math, and engineering behind all of this audio wizardry.